Welcome to an entirely new section of the course, Enumerative Combinatorics. So broadly speaking, combinatorics is just a fancy way of counting things. And we're going to learn some basics of this simple sounding area, mostly through a bunch of problems that are referred to as bin sorting problems. Suppose we have a collection of containers, which we're going to refer to as bins, and we also have a bunch of objects, and we usually call them balls. So we have bins and balls, which might have labels on them. For example, if you have 5 garbage bins, perhaps they're all totally indistinguishable, or perhaps they're labeled garbage bin number 1 through garbage bin number 5, in which case you can tell when a certain one of them has a certain number of objects in it. Similarly, the balls might be labeled. They may have their own letters or numbers on them, or they might be indistinguishable from one another. So for example, we might have 3 unlabeled balls and 2 labeled bins. So what constitutes distinct arrangements of 3 balls that cannot be told apart from one another into 2 bins which can? Well, bin 1 can have 1 object and bin 2 can have 2 objects, but bin 2 could have 1 object compared to bin 1 having 2. Because the bins can be told apart, we can see bin 1 has 1 versus bin 1 has 2. These are different arrangements. Okay? But suppose both the balls and the bins are unlabeled, then these arrangements are actually the same. There is a single bin with 1 object, and a single bin with 2, and a single bin with 1, and a single bin with 2. So if the bins are labeled, these are different because you can see bin 1 has 1 is different than bin 1 has 2. But if the bins have no labels, this is the same thing. There's no distinguishing left versus right. That would be the same thing as putting labels on the bins. The first of these bin sorting problems we're going to discuss, we're going to let n be the number of balls and k be the number of bins. The bins do not have labels. The balls also do not have labels. And we are not going to be allowed to put more than 1 ball into a single bin. In other words, you have a collection of objects and you have a collection of containers. The objects are indistinguishable from one another. The containers are indistinguishable from one another. And you're simply not allowed to put more than 1 object into a single container, perhaps because of space requirements, whatever. Intuitively, what we see is that if n is larger than k, in other words, if the number of objects is larger than the number of bins, since we're not allowed to put more than one ball, into a single bin, this can't be done. This is called the Pigeonhole Principle. This is a old-fashioned way of phrasing these problems where the objects are pigeons and the bins are pigeonholes. If you have more objects than receptacles, and you're not allowed to put more than 1 object into a single receptacle, it can't be done, aka at least 1 receptacle is going to have to get more than 1 object. Also, if you have no more objects than bins, if n is less than or equal to k, there's exactly one way to do it. Just put a single ball into a bin until you've used up all of your balls. Since the balls can't be told apart and the bins can't be told apart, it doesn't really matter which ball goes into which bin. Any such way of distributing them will be equivalent. But in fact, if the balls have labels, nothing actually changes. If the balls have labels, but you still have this restriction that bins can't get more than 1 ball, it's still the case that if you have too many balls compared to how many bins you have, you can't do it. But also, if the bins don't have labels, and your balls are labeled 1 through n, and you just put them into empty bins, well then, just because the balls have labels, since the bins didn't, actually does not change the fact that you can't really tell any difference between how you would do it. So in fact, if there are labels on the balls, as long as the bins are still unlabeled, nothing actually changes here. So we can repeat all that same argument without that restriction, and nothing is different. If the bins are labeled, however, things do change. Just imagine you have 2 bins, call them bin 1 and bin 2, and a single ball. With no label on it, it doesn't matter. But it matters now which bin you put it in, because you can tell the difference between bin 1 having a single ball and bin 2 being empty versus the converse of that. So we're actually not going to discuss for the moment what happens when the bins are labeled. Okay. Now, the pigeonhole principle that we discussed here, that if you have more balls than bins, there is no way to put them into the bins such that no bin gets more than one ball. You can prove this by induction, but honestly, we're just going to rely on intuition. The inductive proof of this takes more space than it's worth. Continuing our discussion of combinatorics, suppose you have two things that you need to accomplish, two tasks. These two tasks are distinct from one another. Okay, so the way you complete one task does not actually affect how you can complete the other. There are n ways to complete the first task, and the second task can be completed m ways. For example, we're going to roll a die. There are 6 ways to complete that task. You can roll 1 through 6, and then we're going to pick a number 1 through 10. There are 10 ways to do that. So the way I roll a die is not going to affect the way I pick a number or vice versa. So the manner in which one task is done, the first n possibilities, is not going to affect the m possibilities for the second task. Then the total number of ways to complete the tasks is the product mn. If I'm rolling a die and picking a number, I could roll 1 and pick 1, or I could roll 1 and pick 2, all the way up to rolling 1 and picking 10. That's 10 arrangements. But then I could roll a 2 and pick the numbers 1 through 10. That gives me 10 more arrangements. I could roll 3 and pick any number. That's 10 more ways of completing this pair of tasks. Overall, it's going to be the product m times n. An inductive proof, again, is possible, but this is a fairly intuitive result as well, so we're simply going to state it. Now, we've actually already seen this result when we were discussing product sets, where A is a set of n elements and B is a set of m elements. Then the product set, A times B, had mn ordered pairs. There were n ways of picking something from A and m ways of picking something from B. Then there are n times m ways of making an ordered pair. This result actually immediately generalizes that if you have a bunch of different tasks, k different tasks, and n1 is the number of ways of completing the first, n2 is the number of ways of completing the second, and so forth. As long as there's no interaction between the tasks, the way you complete one of these k different tasks has no bearing on the other ones. Then the product, n1 times n2 times etc. through nk, which we can write using this product notation, is the number of ways to complete the collection overall. But if there are 0 tasks to complete, it's not the case that there are 0 ways of doing that. If you have 0 tasks to complete, there's actually one way to do it, namely, you don't do anything. So if there are 0 tasks to complete, it's not the case there are 0 ways to do it, there's actually one. So let's move on and consider a second sort of bin sorting problem. Again, we're going to have n balls and k bins. The bins, however, have labels on them, 1 through k, and the balls also have labels on them, 1 through n. But we're not going to put any restrictions on how many balls can go into a bin. It's perfectly acceptable to leave a bin empty. It's also perfectly acceptable to put multiple balls into a bin. We're just counting how many ways can I sort n balls into k bins without any restrictions on how full a bin is allowed to be. The number of possible arrangements is going to be k to the n if n is 0 or k is positive. But if n is positive and k is 0, the result is 0. So as a proof, let's take a look at these sort of extreme cases. If n is 0, the number of balls is 0, there's actually nothing to do. Regardless of whether there are bins or not, we can successfully sort 0 balls into bins by simply doing nothing, and that's the only thing we can do. So there's one solution if n is 0. But if n is positive, I actually have balls to sort, and k is 0, I have no bins to put them in, then there's actually no way to sort the balls into bins because there are no bins available, in which case there's no solution. Otherwise, we actually have bins. K is bigger than or equal to 1, and we also have balls. Okay, n is larger than or equal to 1. If n was 0, we already accounted for that, so n is going to be at least as large as 1. Also, Now that we're on the assumption n is at least as large as 1, if k is 0, we know what happens, so also let k be larger than or equal to 1. So that's where we are. As a base case, okay, if n is 1, okay, we are proceeding by induction on n. If n is 1, there's only a single ball, but we're allowed to put it in any of the bins we want, and that's k possible choices. So there are k to the first possible arrangements of putting this single object into the k distinct bins. Now let's assume, inductively, that our formula holds. If you have n balls into k bins, there are k to the n arrangements. Now let's suppose we have one extra. So we're going to break this into two tasks. Your first task is to sort the first n balls, and your second task is to place the last one. The inductive hypothesis states that there are k to the n possible ways to do the first task, and the base case says if you have a single ball, there are k ways to do the second. Since we assumed there's no restrictions, okay, we don't have to have empty bins or non-empty bins, etc. The two tasks do not interact with one another. The manner in which I sort the first n balls has no bearing on the final ball. So the number of ways to do the two tasks is just the product, k to the n times k, which is k to the n plus 1. So here we have an inductive proof of this general formula. If you're trying to sort n balls into k bins, the total ways to do it is usually k to the n, unless you actually have objects to sort and don't have bins, in which case the result is 0. Okay, but notice, if k is 0, 0 to the n, as long as n is positive, also fits this formula. So the inductive proof was a little awkward in the event that there were no bins, which is why we treated it separately. But honestly, this formula holds for any choice of k and n. The only thing you have to be careful about is if k is 0 and n is 0. In that case, 0 to the 0 is not actually defined, which is why we phrased it as k to the n if k is at least as large as 1, or if n is 0. If n is 0, regardless of the value of k, we're still going to say one possible arrangement. Okay, let's talk about permutations. So earlier we discussed permutations as bijections from a set to itself, but we did mention that permutations come up when trying to count arrangements of objects, and we have arrived at that point. So here's a result. For any natural number, the number of ways to place n labeled balls into n labeled bins, notice now that the number of bins and balls are equal, they're both n. Also, every bin must have exactly one ball in it. The total number of ways to do this is exactly n factorial. So the proof is going to be by induction. If we have 0 balls in 0 bins, just do nothing. But that's one possible arrangement, which is 0 factorial. So now assume that there are n factorial arrangements of n balls into n bins, and suppose I now get one extra ball, but I also get one extra bin. So for your first ball, there are n plus 1, possible bins to put it into. Then what I have, if I've already placed one of the balls, I have n balls and I have n bins. I've used one ball, I used to have n plus 1, so now I have n, and I've used one bin, I used to have n plus 1, so now I have n. Our inductive hypothesis is that the remaining n balls into the remaining n bins can be arranged n factorial possible ways. So for example, okay, here are bins labeled 1 through n plus 1 and balls labeled 1 through n plus 1. My first ball I put into some bin. I don't really care which one. What remains are n balls that are going to go into n bins, and we've assumed there are n factorial ways to arrange them. In other words, I've taken this overall task of putting all of these balls into all of these bins, and I've done it in 2 steps. Put a single ball into some bin, then put the rest. Okay. Inductively, we assumed there were n factorial ways to do that second step, and there are n plus 1 possible choices for the first ball. So the total is n plus 1 times n factorial, and remember factorials obey this recursive property that n plus 1 times n factorial is n plus 1 factorial. So having assumed that there were n factorial ways of doing the distribution when there were n objects in n bins, we derived that there are n plus 1 factorial ways if you have n plus 1 bins and n plus 1 objects. So the proof is complete. The number of ways to sort a given number of objects that have labels into the same quantity of bins that also have labels is exactly n factorial. Let's move on to a third bin sorting problem. Factorials are also going to be used to count the number of ways to place labeled objects in a row. So suppose you have bins labeled 1 through n, and you just want to place them in a row. So you could do, for example, 1, 2, 3, but you could also do 1, 3, 2, or 3, 1, 2, etc. You just have a collection of labeled objects and you want to place them into a row. Factorials are also useful here. Now, we already have established if you're putting labeled balls into labeled bins and you have the same quantity of both and every bin has to get exactly one object, that factorials keep track of how many ways to do that. And that's actually the same problem. Okay, rather than putting a labeled ball into a bin, just consider that to be its position. Okay, so instead of, for example, putting ball number 1 into a bin, you're simply declaring that bin to come first. Instead of putting ball number 2 into a bin, you're considering that bin to come second. So ball label can be changed in your mind with order. Every bin must have a position in the order, but it can't have more than one, is equivalent to every bin must get a single ball. Depending on the particular flavor of a problem, division might be necessary to avoid overcounting. For example, how many ways can you arrange n-labeled bins into a circle where relative position is what matters, not absolute position? So for example, what I mean by this restriction, if I want to arrange 5 objects, these two arrangements are the same. Because if I start here, I can call this 1, 3, 4, 2, 5 by going in the clockwise direction, 1, 3, 4, 2, 5. Now, if I started in the same position, it would look different. But if I start here and go clockwise, I still see 1, 3, 4, 2, 5. This arrangement is just a rotation of this one. If I rotate this 2 steps in the clockwise direction, I'll just end up here. So since these are rotations of each other, while their absolute positions have changed, their relative positions to one another have not. So these are considered the same arrangement. These, however, are different. Okay? If I tried to start here, I would see 2, 5, 4. So 5 comes after 2. Now, if I start here, I would go 4, 3, 1, 2, 5. 5 still comes after 2, directly after it. In this arrangement, however, 2 would come directly after 5. No matter where I started, as long as I was going in this direction, 2 comes directly after 5. Here, 2 comes directly before 5. Their relative positions have changed, so these are considered different arrangements. So how many ways can I arrange n objects in a circle with this sort of restriction? That rotation changes are not considered to be different, but if you change where things are in relation to one another, that is considered different. Well, our problem is arranging n-labeled objects into a circle, where rotating that circle does not create new arrangements. Okay, so what we want to do is we're going to designate a certain spot as first, and then count in a particular direction from the first spot. So this actually transforms the problem into something we've already done. How can I arrange n objects in a row where I have a first through last? Well, there are n factorial possible ways of doing that. We've already established that. But now we've actually overcounted the total number of arrangements for our circle problem, because each possible arrangement of things in a row could be the same circular arrangement. So for example, take a look at this diagram. We're going to consider the top spot to be first, and I'm going to go in clockwise direction. Then this would be 1, 4, 2, 5, 3. As a row, 1, 4, 2, 5, 3. But all of the following diagrams could also be the same circular arrangement, 1, 4, 2, 5, 3, 1, 4, 2, 5, 3, 1, 4, 2, 5, 3, 1, 4, 2, 5, 3, 1, 4, 2, 5, 3. But if I specifically was designating the top location as first, they would generate different rows. If I specify the top as first, here's our original 1, 4, 2, 5, 3, but this now looks like 3, 1, 4, 2, 5. It's a different row arrangement, even though as circular arrangements they're the same. All of these are different rows, even though as circular arrangements I want to be counting them as the same. So each row is actually 5 different circles because, in fact, there were 5 different positions I could have considered as the first one. So we've actually counted everything 5 times. Okay, every circular arrangement has been counted 5 times. While these are all the same circular arrangement, I would have counted them as 5 different rows. Because there were 5 different positions that I could have considered as first. Here, if I considered top first, I got 1, 4, 2, 5, 3. If I considered this position as first, I would have gotten 4, 2, 5, 3, 1, which I found here as this row. It's the same arrangement, just rotated. Instead of considering this first, here we'd consider the top first. Similarly, if I considered this spot to be first, the same circle would have given me 3, 1, 4, 2, 5 that I would have seen here. It's the same circular arrangement, but if I consider the top to be first, this gives me 3, 1, 4, 2, 5. So because there are 5 spots that I could have considered as the first one, I get 5 distinct rows from the same circle. So I've overcounted everything by a factor of 5. So continuing with this problem, if I sort n labeled objects into rows, each circle had a factor of n over counting, okay, for each possible rotation of it. So we've actually overcounted by a factor of n. There were n factorial arrangements into rows, therefore there are n factorial divided by n. I need to divide out the factor of n that I've overcounted. So there are n minus 1 factorial arrangements of n objects into a circle. As long as you didn't start with 0 objects. If n was 0, this is 0 for emphasis, not 0 factorial. I recognize it can be a little confusing. So for 0 objects, there's still a single possible circle, just do nothing. But I can't talk about -1 factorial. We've already discussed that value simply doesn't exist. So we would say that the number of circular permutations, in other words, arrangements of such things into a circle, of n objects is n minus 1 factorial as long as you actually have objects, and then we simply manually declare that 0 objects can be circularly arranged in a single way, even though we're not going to call it 0 minus 1 factorial.